Thanks for coming to this talk. I've already given a talk yesterday. I'm curious, who was here at my talk already yesterday? Oh, wow. Thanks for your faith in me and coming back. I was afraid no hands would be coming up. So it is there will probably be one of the other slides which you have seen yesterday, but the focus today is totally not on observability, but more about generic things on how to handle distributed applications. A lot of people might call it microservices now these days. I don't want to limit it particularly down to microservice. It's basically for any kind of distributed applications and technologies that support it. All right, a quick word about myself. So for the new ones in here, my name is Matthias. I come from a small software consulting company called Novatech. We do custom implementation with modern cloud native practices. And next to that, I'm also teaching at 2 universities exactly in this very field, like distributed systems. And what I tried to do over the last couple of years is try to convert it a bit into like modern distributed systems, like a lot of hands-on in this lectures to show the students what are the current technologies around, how people build distributed applications, and most importantly, why would you actually build them? Now, just a very quick advertisement of what my company does. So basically, I would say we do the entire life cycle of like a modern software engineering world. That means like agile consulting on the team side, starting with here, then build modern applications, run on modern technologies, automate all the things. And the 2 kind of areas that we're going to look in today is basically either how to build the applications, like using frameworks and putting stuff in there for making the application running well in a distributed world, or on the other side, using platforms like Kubernetes and putting things in there. When I created that talk in the first place, I did that for the Spring I/O conference in Barcelona. It was mostly limited to Spring and Spring Cloud. The thing that I've changed over time was adding also information about Quarkus, Micronaut, and other frameworks. So I just saw a Micronaut t-shirt sitting here. So I'm glad I have it in there. Also, of course, I mean, I probably won't be able to cover each and everything. So if you have the feeling at the end that there is something significant that I forgot or should mention in the future, please let me know. So, but anyways, these are the things we're going to look into. That's also what the title says, using frameworks or Kubernetes with service meshes and eBPF, basically to get a better control of your distributed application infrastructure. So, as I said, I'm going to start with why would you do things in the first place, then basically how can you do it, and what can you use to basically implement the how. And these are the 4 things that I have just explained, and then wrap it up with some kind of conclusion. So already as of now, I can say I'm not here to pitch any of those things as better or worse. It's more about making sure to show the available option and also give everybody a feeling, okay, this is what you need to change in order to have a certain kind of outcome. All right, so most people will probably be familiar with that, but in the end, why would you start breaking your application down into several pieces? I mean, in the end, it's all about to make your clients happy. And the clients of your applications, they should probably not even know that the architecture is distributed or not. It should be just as a pure one system to them that provides the functionality. It's like if you open a Google email or map, you probably don't wonder how many containers are running underneath. And that's exactly the same thing, how it should be everywhere. So in the end, this is how it looks like for your consumers, and this is how it looks like for you. Now, the main reason is probably why if you like a heterogeneous factor to say you have multiple different tasks, you might want to run them in parallel, you might want to run them independent, so you put them into individual systems. Other reasons might be you have different underlying operating systems, so Unix, mainframe, Linux, Windows, whatever. So that means you can't run them all on the same stack. It's another reason for the distribution. Something we see very often nowadays is, I just mentioned microservices, but having a polyglot application framework. So picking basically the right technology for a certain part of the application and bridging them all together. container technology is very helpful to support that. So these are kind of like application structures that we see very often in our customer scenarios. And it doesn't even have to be entirely polyglot. Even if you just have like different versions of Java, different versions of a framework, they won't be able to run on the same stack. So you have to break them out into individual components. And this is actually, as a side note, that this slide was not in there originally, but this was one of my students actually said that to me, and said, you might also want to have different autonomous development teams to work on a single component without interfering with each other. So I was pretty impressed by his advanced way of thinking as a student, so we hired him. And I put, as in an honor, I put the slide in this deck because I think that was really nice. Other things are, of course, you want to grow the system over time. You probably don't want to rebuild everything and redeploy everything with every iteration. So making it easier extensible without affecting everything is also like a heterogeneous factor. The other factors are more under the umbrella of, let's say, resilience. So another form of distribution is to say, I want to scale my system to a couple of instances. So if one breaks, my clients will still see a happy and like a healthy and happy application. Also, if my clients increase over time, I would want to scale up to say, okay, I want to distribute the load to make everyone happy. And if they get too much, I also might want to have some resilience mechanisms in the system to say, I either want to block or maybe throttle the traffic so that my systems still remain healthy and not like the load will take everything down. I mean, this it's not always like friendly users. It could also be like a denial of service attack. And this is something, of course, you want to prevent to be harmful to your environment. Security, of course, make sure only the allowed requests which are entitled to reach the systems are getting through. And updates. I already mentioned that before with extensibility. Something we, of course, do very often is things like a blue-green updates. Say you deploy a new version on exactly the environment where the old version runs, and then shift the traffic to the new one while the old one is still running. That makes a dynamic switch and also a good possibility to fail back to it in case the new version didn't turn out so super well. An advanced form of that is like a percentage routing, or often also called like as a canary deployment, where you deploy the new version but don't switch like over entirely. So you can do that either like on a percentage level or like on a request level to say, like Facebook or like major companies do that. They roll out a new version, and based on the request, they can say, okay, this geography is getting the new one, and the other ones are still basically running on the old one. And if things are working fine, they migrate it slowly over. Right. So there are probably more things, but I think you're going to get the point. These are all factors why you potentially would want to adopt such an architecture. If nothing of that applies to you, I would actually not recommend to break things apart and still run on a single system. But very often, these requirements are there for critical applications. So what you need is, of course, a network. You need the applications to be able to communicate with each other. You also need something like a telephone book or like service discovery or a registry, how it might be called. So if a new service joins, it will say, okay, I'm service X. And when another service says, is there a service X? The telephone book will say, this is the address, and then they can communicate. In addition to that, distributed configuration is an important thing that you may want to update parts or all of your instances over time. So you need mechanisms to push that configuration out. Distributed logging and tracing is another factor to basically find out if things go wrong, where they are going wrong. But as I said, if you really are more into that, I would recommend you to watch my talk that I gave yesterday, because that was exactly about that part. In the end, you need some mechanism. I made this little diagram here. Okay, this is like my routing, traffic, shaping component that can either route, distribute, throttle, or block the traffic. And with that kind of mechanism, I'm able to handle the communication flows between my components. Now, this is like how a simple example could look like in kind of an API or a proxy server in the beginning. Then we have multiple applications, potentially talking to persistence mechanism, and having them all connected to a registry, configuration, observability mechanism. You can already see that even in this small scale, it has a lot of implications and a lot of things you basically need to be aware of and cover. But with that, you are then able to say, now I can do different version rollouts of a certain part, or I can scale the application up, and I can load balance between the service, and basically get to the points that I mentioned before. Now, one of the companies that had exactly such an architectural problem was, or is, Netflix. And I didn't know that for a long time, but Netflix originally was not running as a distributed application, but it was running as a monolith. It didn't scale very well, so people started thinking about how can they decompose that. And Netflix in 2015 brought out this open source collection of the things that I just mentioned, like a service registry, a configuration server, resilience mechanisms, and so on. Parts of those still exist today, but this was kind of the start, and that also brought a lot of popularity in the world of like microservices, and gave people a starting point how they were able to adopt that. So they were using that routing traffic shaping component in different ways. So like placing a routing mechanism here, a distribution mechanism here, blocking or throttling over there. So with that, you could basically mix and match and say, this is the functionality where I need it, and that's where I'm going to place it in my infrastructure. Spring Cloud kind of originated out of that. So I think the teams at that time worked together for a while, and Spring Cloud adopted a lot of the Netflix ideas into an own open source model, which was called Spring Cloud. A lot of those, and initially they also had very similar names, but over time they changed. So I think Zool was an API gateway for a while. This is now called the Spring Cloud Gateway. Then Hystrix was sometime like seasoned, and then it was replaced by Resilience 4J. Other components are definitely still around. So with that kind of adoption, you could say, okay, I'm going to build my distributed application landscape and use the components that I need. The way it works here in Spring, and it works pretty similar in other languages and frameworks too, is basically that you need to add the dependencies of a certain component. In this case, it's, for example, the Eureka server, which is, like I said, the telephone book. So you add the dependencies in the Maven or Gradle definition, and in the code with a simple annotation, you're good to start. In a similar way, it works from the client side. You basically have now the dependencies for the client behavior, and then you have the annotation of enable discovery client, and then when it starts up, it will connect to that Eureka server and say, okay, this is the name that I have. Please register me under that name. And I also have the possibilities then to query other services in that registry. As I see people taking photos, I think the Spring Cloud starter config, or like one of the dependencies here, is not accurate anymore. I think the name has changed. This is not a text, this is a picture, and I wasn't able to correct it prior to this talk. The other ones are still in the same way. So the Spring Cloud Starter Gateway is still called that way, and this is the way you would implement that. And then you can use that configuration to say, this is the way I want to route my traffic. Yeah, so I'm not going to go through all of them. I think you kind of get the point. And so the way it works, they run then as the inside of this Java process, and that gives you some certain flexibility. I mean, you can run everything as an own process on the same machine. You can, of course, run everything on an own machine. You can run everything in an own container. So you really decide on how to place the environment, and you're totally independent of the underlying infrastructure. So you don't need Kubernetes or Docker or anything else. It's really about just the process, and you add the components to it. All right. Now, coming to Micronaut and Quarkus. They have similar approaches. So with Micronaut, actually, if you go to that Micronaut launcher, you have the possibility to say, okay, I have Discover Eureka or Netflix Arceus or Hystrix that I can use. So they basically still implement and use the Netflix original ideas, but they also have others. So if you go on that launch, you say, okay, under distributed configuration, I have various options. Under discovery, the same thing. And for, let's say, the resilience mechanism, you can, of course, use a generic library like Resilience 4J. I mean, this one is independent of any of the frameworks, but it says it's a fault tolerance library for Java, where you can have things like a circuit breaker, a rate limiter, retry, or a bulkhead, basically things that makes, as the name says, your application more resilient. Quarkus has actually a different approach. They are using a library collection called smallRye. This originates out, I think, initially from the Eclipse microprofile world, but it's also adopted by OpenLiberty and Wildfly. So they have also libraries that you can add and put into your application for service discovery, config, health, tolerance, and so on. So you see the concept is basically fairly similar across all the frameworks. Some have a more like built-in into the local ecosystem like Spring. Some use like open libraries to get to that. But in the end, it's your choice what you're going to put in. And you also have the freedom to say, well, this is what I want, and this is what I don't want. I think here, this is all what Resilience for J says. You don't have to go all in. You can pick what you need. And this is, in my opinion, the significant advantage here. All right, so to sum it all up, this all works on an application level, mostly as a combination of a dependency, code, and configuration properties, and it's totally transparent to where the application will run in the end. So you can start building with it in an OS process, put it into a container later, or run it on Kubernetes. It totally doesn't matter. You're independent of that. And you have, as I said, the possibility to pick and choose what is the right thing for you. Now, one of the reasons also why Micronaut and Quarkus might not have such a big function scope inside of their own library as Spring, for example, with Spring Cloud, is also the fact that they were released after Kubernetes was already present. And we're going to see in a second that Kubernetes also already provides a couple of things out of the box which make those functionalities obsolete. So you could potentially say, and Quarkus in particular pitches itself as like the Kubernetes kind of oriented framework for Java. So they certainly rely a lot on this functionality. Now, who in here is not familiar with Kubernetes? Okay, that's good. That's the reason why I asked it this way. So, I mean, I teach a lot of Kubernetes classes, and I know it's hard in the beginning. So in an easy way, I would just say it's a distributed container daemon. So it's like it runs on a distributed architecture where you can basically run your containers in a scaled and load balanced way. Now, Kubernetes has some own API objects, like a deployment or a pod or a replica set or a service, and most of them have some kind of this functionality that I was referring before already implemented. So Kubernetes, for example, and sorry, I was a bit too quick. And the concept is basically running everything in a pod. So a pod can be seen just like as a container around a container. It's like the smallest deployment unit that Kubernetes handles. So everything in here with that dotted line is basically running in its own pod. Now, if we, for example, look at this service type here, the cluster IP, that actually fulfills two different, like a Kubernetes service fulfills two different purposes. So the one thing is it registers the application in the service registry. So it gets a name in the cluster, like in the DNS, so it can be reached from everywhere in the cluster under that name. That also means a service can will look up all the instances and then route the traffic to it. So the amount of instances is actually defined by a replica set. So a replica set, I can say I want 3 instances, and then I expose it as a cluster IP service. And this cluster IP service will not only register it, it will always load balance the incoming traffic across all present instances. So even if they scale up and down, the service does not need to be updated. It will automatically detect it and provide that load balancing mechanism. So these are already 2 things that come, in this case, from the platform side that you don't really have to put into the application and use frameworks anymore. Other things are external configuration. So Kubernetes has this concept of config maps and secrets, where you can basically place the configuration outside of your object and reference it from there. So it is pretty obvious that this is like kind of the idea for Kubernetes in the first place, to be prepared for all the distributed application problems and provide answers for that, and making the applications more resilient in such a context. Now, if you have already built your applications before Kubernetes, for example, with Spring Cloud here, it probably doesn't make sense to use two different discovery services. Like Kubernetes provides one anyway, so there's probably no reason for you to do build another one in there. For that special case, Spring Cloud has also a dependency called Spring Cloud Starter Kubernetes, where you can leave the code as it basically is, but just point it then to use the Kubernetes service registry. So in that case, you can do a simple upgrade and say, okay, this application runs in Kubernetes now. Then I don't really rely on Eureka anymore, and I can use that in the future. Same thing goes for the config map. There is also, you can use that with the configuration properties, as you do with typical external configuration in Spring or Spring Boot anyways, and now just reference the content from a config map. All right, so as you could see, or as I have mentioned, Kubernetes provides things like scaling, load balancing, service registry, external configuration, totally independent of the framework. So in that case, you don't have to put it into application, but you need to use Kubernetes in order to get that functionality. So you basically outsource that responsibility to the platform. However, it doesn't match all of the functionality that the libraries provided, which I have mentioned before. So configurable routing, network traffic awareness, resilience mechanisms like circuit breaking is not built into Kubernetes. So this is still something you either have to implement through the application frameworks or extend Kubernetes. There's two ways to do that, or currently two ways. And they both kind of belong under the umbrella of the kind service mesh. So one type is the, let's say, pod-based service mesh. I've mentioned the pods before, so a pod is like a container for a container. The reason why it exists is that Kubernetes can basically put multiple containers into a pod. What that implies is that all of the containers here share the same IP address and the same port range. So they can communicate with each other via local host. And it also means one part will always see the traffic that the other one also sees. It doesn't make a whole lot of sense to put multiple applications in there, but now putting this kind of traffic shaping component as a proxy into my pod makes actually a lot of sense, because with this one I can now say, okay, I want to monitor that traffic, or I want to block that traffic, or I want to encrypt that traffic, because the proxy provides that possibility. It doesn't provide the possibility if I put it only into one pod, but it does if I put it into every pod which is running, because then I kind of have the full control of all the network traffic flow in my cluster. And this is, of course, totally independent of any language or framework. So like all the examples that I had before, and as we are on the JVM track here, are Java-based examples, but they wouldn't be able to be applied to like a Vue.js or a Go application. Now, with the service mesh, this can be circumvented in an elegant way, because you basically put it into that proxy and put it out of the application. The other advantage is you can easily put it in and out. So you don't really need to rebuild your application. You don't need to rebuild your container. You can just like add it to it. It will only require a restart of your pod. Right. So what this basically means, if this was what Kubernetes was looking like before, we basically extend the pod and then add this component everywhere in there. There you can also see the drawback, because it suddenly has to be everywhere. Especially if you have a scaled application, it's not going to be one time per application, it's one time per instance. And then the component it basically connects to is called the control plane. So you suddenly have all those connections now in there. This is why it is very often also referred to as a service mess instead of a service mesh. And this is a layer that you have to maintain. But it will give you all that possibilities. I mean, you can go now in and say, I want to make sure this traffic between this component and this component is now encrypted, or only those components can communicate with each other. This is something you can do to a certain extent with network policies in Kubernetes, but in an advanced way to really limit it all down is only possible like that. So you can say, okay, if this one matches the source label, then it can only be connect to those hosts over that port, and no other traffic is allowed. The other thing I mentioned before is that this dynamic routing, where you say I deploy a new version and then I only want a certain percentage of it. This is also possible like this. So you can just say I have 2 destination routes, and this one I give a weight of 75%, and this one I give a weight of 25%. And I can gradually change that. So if I say, okay, then the new version is actually picking up well, I can basically route more traffic to it. I can increase that weight without affecting any of the applications at all. So yeah, this there's a bit of a price that you pay because you have to inject all those proxies in there. But in the end, you get a lot out of it. I mean, it's not only, you can not only route based on percentage, you can also say maybe on cookies. So I just recently there was a new update of Google News, and they asked me, would I want to try the new version or would I stick with the old one? And if I select new, I basically get this cookie set. And then the API gateway will decide, okay, if that cookie is set, route it to the new version, or basically stick with the old one. These are all things that you can do in there. You can even take it to a limit of chaos engineering and say, I inject faults deliberately to see how does my application react if a certain network times out or is broken for a while. So technically speaking, you kind of put like a mini API gateway into each and every of your pods. So you get a lot of functionality. If you need it, that's basically, I cannot tell this. This is basically what you need to decide. So also that possibility to say, I want only a retry mechanism here, or I want only a load balancer here. This is not possible. I mean, once you have that proxy in, you have everything if you want it or not. Yeah, one side effect which you can get kind of out of this is observability, because once you control all of your traffic, I mean, the first thing you get is like insight of what is actually happening. And here is just an example where I say, okay, I have 2 versions of this to-do component, 0.2, 0.3, and I can now visualize that traffic, how it is being split, what is the percentage between them, is everything going fine, and so on. I mean, it probably doesn't make sense if you have an application of that scale to put a service mesh in, but if it's like bigger ones, of course, it can be very helpful to see, are there things being highlighted because there are errors, and also to read such a graph, you don't need to be a Kubernetes expert. This is probably also something that a higher level manager would understand without looking into any kind of YAML code. All right, but the price is a bit of overhead. So this is a bit of an old data. So there was a benchmark being done in 2021. This has certainly changed and improved over time. I also don't want to go into the exact numbers and percentiles. It's just you need to be aware that if you had the situation before that service A was connecting to service B, now A is connecting to proxy A is connecting to proxy B, and proxy B is connecting to B. And that will not make your connection faster. So this is something you have to basically figure out for yourself if you're willing to pay that price. In the end, I mean, it's easy to try out. So that's what I always recommend. Play with it a little and see if it does the job for you. All right. I think what does the time say? A few more minutes. I'm getting somewhat to the end. Yeah, this service mesh basically extends Kubernetes for the limitations in traffic awareness and traffic shaping. And it's based on the concept that you inject this sidecar component like into this proxy into a pod and then get more control over the network flow. However, I mean, you don't get anything of the application, but you can change the configuration at runtime. There is no built kind of affinity that you have to rebuild any of your components. All right, now the final one, which I have on my list here, is called eBPF. Who in here has heard of eBPF? Okay, there's not so... Okay, there's a few hands. This has the very meaningful name of Extended Berkeley Packet Filter. So it doesn't really sound like a service mesh, whatever, Kubernetes extension, distributed thing. It's more like a low-level network component. That's where the name filter comes from. So a quick excursion to the Linux side of things. So most of you will know that Linux has a so-called kernel and user space. So the kernel is where all the critical processes run. This is something what you shouldn't touch. And the user space is where you install your applications and where you work and do all the things. Now, eBPF is basically a mechanism how you can inject code into the kernel while it is running. This sounds very dangerous, and it potentially is, but eBPF has a thing called a so-called verifier, which checks the code before it gets injected into the kernel, so it can't do any harm. A very easy kind of analogy I have heard, eBPF is something to the Linux kernel what JavaScript is to a web page. So you put the JavaScript in, your web page can do more things than before, but it's still not able to break out of the browser and onto your local host system. And once this code is running, it can basically grab all the kernel events, hence the name filter. So it can also grab network events. And that basically gives the possibility to intercept all the network traffic on a way lower level than we have seen before in that pod example. So most of you, as nobody raised their hand before, I think you are aware that Kubernetes has worker nodes, and those worker nodes mostly run on a Linux operating system. That means we have underneath all the Kubernetes things like the proxy, the kubelet, the daemon, and so on, there's a Linux running, and that means we are able to use that eBPF functionality by injecting the custom code into the worker nodes of our cluster. This is a simplified way of putting it. So basically, you have that eBPF or proxy component, whatever you want to call it, and put it on your nodes. Similar thing as with the pod-based service mesh before, you have like the control plane to see and control everything, and you have the data plane where you collect the traffic and basically set the control commands to. The big difference most likely is that people tend to have a lot less nodes than pods in their environment. At least you should have it that way. And that means the overhead for placing that collector component is lower, and the performance can be better then. So looking back at the diagram we had before, so instead of placing our routing traffic shaping component into each pod, we now place it into every node and connect the control plane to that. Function-wise, they can pretty much do the same things. And so that gives you the possibility to operate on a similar level without touching your pods. So this is an example for a Cilium, is one of the technologies, a Cilium network policy, where you can then say similar thing as before. Like some of the pods are only be available from pods with another endpoint, or matching labels, or matching ports. This is basically all under your control. It's just an equivalent to the example that I have shown before. Yeah, so, well, I'm going to skip that. Again, observability is also like an outcome that you can have here. So this is like a topology graph of an application running in there. So once you have that eBPF kind of functionality enabled, you're also getting the information about all the traffic flows and then can start to control them. So yeah, this has been probably one of the rather hot topics in the Kubernetes or CNCF world in the last 2 or 3 years. It has grown quite a bit. The concept, as I said, is in using that Linux low-level functionality, which has actually been around for quite a while, for in particular Kubernetes. You can actually use it outside as well. You can also use service meshes outside as well. But for this talk, I'm just going to pitch it in that way. I say that this was mainly being built as an extension for Kubernetes, and this is where we see the highest adoption. We have lower latency because we have less hops of the traffic that it has to travel. And yeah, it's network security and observability are the things which are basically covered by adopting that. So in the end, which one is right or which one is wrong totally depends on you and your architecture. I mean, to recap, it has all the Spring logos in there, but again, this could be Micronaut, MicroProfile, whatever, because they work all in a similar way. This solution gives you the possibility to say, I might not need the full function scope, and I want to place it wherever I feel it is right. But the downside is you then have to touch the code and change the code in order to do that. So there's a recompilation, a test, and the build necessary. With Kubernetes, you basically take it out of the code, but you basically then depend on the platform. So if your applications are not running in Kubernetes anymore, then you don't have the functionality. So it basically ties you into that ecosystem. If it's not enough, you can extend Kubernetes with either sidecars or eBPF to basically get the full spectrum of functionality that frameworks can give you as well. All right. If you want to have these slides, this is a link to my to the presentation. I think I have 2 or 3 minutes left. This one, I didn't think I'd get through it too quickly, so I hope I wasn't rushing too much. But it certainly allows me to answer a few questions if you have any. But before questions, I would first of all say thanks a lot for listening.